Again, hi everybody, welcome to this afternoon session. And it is a pleasure to introduce Nick Gurski, that he will speak about towards two-dimensional Tannaka duality. So Nick, please.
Thank you very much. Thanks to the organizers and for everybody who's here right now or watching this later on the recording. So this is some joint work with David Yetter that is still in progress. I wanted to start by talking about the kind of TQFT side, which while maybe not as important to me, is a big reason that I convinced David to actually do this project with me. This is my not a definition of what a TQFT is. It's a thing where you take manifolds and then you get back some other invariant that you think of as algebraic, and you do this in such a way that it's compatible with chopping up your manifold. So if we look at my beautiful pictures of two-dimensional tori, then that's a closed two-dimensional manifold, and so a TQFT you think of as giving you morphisms from the input boundaries to the output boundaries. Closed means there's no boundary, so the input is just the sort of ground field K that you're working on. The output is also the ground field K. In other words, this TQFT is supposed to assign a number to the torus, and if we chopped our torus up in a number of different ways, we're supposed to get the same answer. So this version on the left, where I've just done a single cut down the middle and kind of glued two pieces of macaroni together, should give me the same version as the one on the right, where I have a kind of hemisphere and then a pair of pants and then a dual pair of pants and then the other hemisphere. Okay, so how do you make a TQFT? Well, this is how I think about how people make a TQFT, which is that you feed it some kind of algebraic input usually, and then the TQFT is a recipe for then taking a manifold and getting some algebraic output, like a number. So the classic theorem that everybody cites is this this classification of two-dimensional TQFTs, two-dimensional oriented smooth manifolds. If you look at TQFTs on those, they correspond to commutative Frobenius algebras. So here, fitting this into my sort of standard methodology rubric, the commutative Frobenius algebra is the algebraic input, and then the TQFT says, if you give me a manifold, I can give you some kind of information back. So maybe that's a number, or maybe that's just a morphism between some vector spaces. So this is kind of how people, well, maybe I should say how algebraists, I think about making a TQFT. So what am I actually going to talk about? Crane and Frankel wrote a very, very sort of sketchy paper a long time ago, where they suggested that if you wanted to make some 4D TQFTs in this kind of hands-on way, then what you should do is you should make up a thing called a Hopf category. And this is kind of a boosted up version of what they had seen from three-dimensional TQFTs, where you could take a Hopf algebra and you could use that to make a genuine 3D TQFT. So they suggested you should try to make these Hopf categories, and then you should keep going and figure out how to make TQFTs from them. That was their recommendation. So then you say, how do I get a Hopf category? And they said, well, why don't you back up a further step and make up another thing called a tri-algebra? And this is going to be like a ring, but with more operations and co-operations, kind of similar to the commutative Frobenius algebra that we had for the 2D TQFT case. So you should figure out how to make these tri-algebras. Once you do that, then you'll know how to make Hopf categories. Once you do that, you'll know how to make TQFTs. So this is a kind of involved process. They didn't solve any of these problems. Now, where we come in is I suggested to David that we could try to sort of reverse engineer this notion of a tri-algebra as an instance of a higher dimensional version of Tannaka reconstruction. And so I'm going to try to tell you kind of like how these things fit together without getting into too many of the really technical details, and kind of what we know, what we don't know, which is still quite a lot. That's the purpose of this talk. So I'm going to do 4 things, or at least my goal is going to be to do 4 things. I'm going to talk about this classical Frobenius algebra example just a little bit more. I'm not going to get into great detail. Then I'm going to talk for a little while about a kind of easy genesis for Tannaka reconstruction, thinking about just categories of representations of groups. Then I'll tell you a kind of very basic version of how you might do Tannaka reconstruction in the classical case, and then outline what David and I have been thinking about in a kind of 2-dimensional version. Okay, so Frobenius algebras. So we're going to work in the completely classical setting. So we've got a field K and we've got vector spaces over K. And then the definition of a Frobenius algebra, this is one definition, is that it's a finite dimensional algebra over K, and you equip it with a non-degenerate bilinear form sigma, which has this further property, that if you do sigma of x times y with z, then that's the same as sigma of x with y times z. Okay, I said this has lots of different reformulations, so sometimes people like this kind of less ringy looking version with this k-linear functional, or they like a more diagrammatic version, which is that you could think that a Frobenius algebra is an algebra together with a co-multiplication delta, which satisfies this equation, that if you do delta on x times y, then that's the same as doing delta of x and then multiplying the second coordinate by y. So this delta 1 of x tensor delta 2 of x. This is this notation for how you write things down in a tensor product, where I've suppressed the sum. So delta 2 of x is the stuff in the second tensor factor. And that's the same as if you took x and multiplied it with the first factors from applying delta to y. So these equations, you can just write them down in any symmetric monoidal category that you want, because this is purely about the interaction of some morphisms, where all we've used are the tensor product and the fact that a multiplication goes from A tensor A to A, and a co-multiplication goes from A to A tensor A. So you can do these Frobenius algebras in any monoidal category that you like, and if you want to do some more things, like I mentioned, commutative Frobenius algebras, then you should do symmetric monoidal categories, et cetera, et cetera. Okay, if you want some examples, classical ones are matrices, where the bilinear form is a trace or a group ring, or maybe the most relevant here, although we're not getting into any of these, is that any finite dimensional Hopf algebra is automatically also a Frobenius algebra. Okay, so those are just Frobenius algebras. What does this have to do with TQFTs? Well, Atiyah had this reformulation of TQFTs as symmetric monoidal functors. So a 2-dimensional TQFT is a symmetric monoidal functor from the symmetric monoidal category 2 Cobb. The objects here are 1-dimensional manifolds, and the morphisms are equivalence classes of cobordisms, which is to say 2 manifolds between them. So a 2-dimensional TQFT with values in your favorite symmetric monoidal category C is just a symmetric monoidal functor from 2 Cobb into C. And this classification theorem of Abrams just tells you that actually 2 Cobb is the kind of universal thing that has a commutative Frobenius algebra object in it. If you want to be fancy, this is called a prop. So you just take a symmetric monoidal category and you put down a thing that's going to be a commutative Frobenius algebra, and you just keep going from there. So you have to have tensor powers of it, and you just have to adjoin the morphisms coming from the symmetric monoidal structure and the things you need to actually support that commutative Frobenius object structure. So if you're the on the kind of like cobordism hypothesis side of thinking about TQFTs, then this is the kind of thing you're thinking about, which is to say it's not actually what we're thinking about. We're kind of more on the like algebraist side, which is to say I want to provide you with something, and then we'll get an explicit recipe for what to do with it later. Okay, so that's kind of a reminder about how these Frobenius algebras kind of show up in the classical story of two-dimensional TQFTs. Now I want to talk a little bit about basic representations of groups. So this is just the most basic version of the definition of a representation of a group. You get a function from G cross V into V, and then you've got some axioms. And then we get a category of these things, rep G, and the morphisms are just the linear transformations that preserve the G action. Okay, now for a lot of purposes, it's really better to think of this in an alternate form, which is to say we can take the group G and we can make a category BG, which has a single object, and the automorphisms of that single object are the elements of G. Multiplication in G has been transmuted into composition of morphisms. And then rep G is just isomorphic to the category of functors from BG into vect. If I give you a functor from BG into vect, it sends the single object to some vector space. That's the vector space you're going to act on. And then the automorphisms in BG get translated into automorphisms in vect. This also means that if you didn't want to do representations of your group in vector spaces, you wanted to do them somewhere else, then you would know what to do. You just replace the category of vector spaces with your favorite category. So one of the reasons I wanted to mention this is that I think it's useful to put sort of TQFTs and representations on the same level, because when we're talking about TQFTs, we're doing the same kind of procedure here. We've just replaced BG with something like 2cob, and maybe instead of doing all the functors, we're thinking about just the symmetric monoidal ones. But it's fundamentally the same kind of procedure. Okay, so here's a slightly silly exercise, but it gets us to the place that I want to go, which is Tannaka reconstruction. So you have to pretend that you're thinking about G sets. You've decided you want to investigate the category of G sets for some specific group G, and you've thought about it for long enough that you actually forgot what G you were thinking about in the first place. But you want to get it back because later on somebody says, oh, well, what group are you working with? And you say, I don't actually care that much, clearly, but I can figure it out for you. So how do you get the group G back out of the category of G sets? So here's a theorem. You take your category of G sets and you look at the forgetful functor back to sets. And you call that U, and you look at the endomorphisms of that functor. And the theorem is that the endomorphisms of U form a group, and that group is G. This is just the innate lemma. It's a great exercise for kind of introductory category theory students. What are the key points here? Well, the most important feature is that the forgetful functor from G sets to sets is representable, and it's represented by G. So the endomorphisms of this representable functor will then just be maps of G sets from G to G, and those are just elements of G. Okay, so this is how you would get the group back if you forgot which group you are working with, and this is the most basic version of Tannaka reconstruction that you can possibly have. Nobody actually, this is not a challenge, but it sort of sets the groundwork for what will be a bit more interesting. So let me try to remind you or tell you for the very first time a little bit about Tannaka reconstruction. So here's the kind of classical setup. We're going to mimic a lot of things from this G-sets example, except with a little bit of change. So we're in a kind of linear world. So we're thinking about like modules, but for technical reasons, we're actually thinking about co-modules. So we have a co-algebra and it's got co-modules. And we want to do this kind of exercise where we forget what co-algebra we're working with and we want to get it back. So that means you give yourself a category C and you suspect for whatever reason that C is the category of finite dimensional co-modules over some co-algebra A. And since these are co-modules, well, that means they must have an underlying vector space. So you've got a functor U from the category C to the category of finite dimensional vector spaces, which forgets the coaction that you can't quite remember anyway because you don't know what the co-algebra is. That's the setup. And you can ask yourself a variety of questions. So the first and most basic is, how do you get A? How do you get the co-algebra A back for which C is the category of finite dimensional comodules? Now, if A is a finite dimensional comodule, then we basically just repeat the G-set kind of example. But a much more interesting version, and this is the one that kind of comes up in algebraic geometry and representation theory, is, well, what happens if A is not finite dimensional? The key fact we use for the G-sets example is that it's a representable functor. In other words, G is in your category. But if A is not finite dimensional, then A is not in the category of finite dimensional vector spaces. So you have to do something else to get it. And finally, what else can we learn about A? Like, does this amount of information reveal something about A that maybe we didn't know before we started? Okay, well, the way you do this is with a co-end. So recall that if you've got a functor from C op cross C into D, which I'm going to call F, then the co-end of F, which is written with a little integral sign, is a universal object that comes with some morphisms where we repeat the kind of object variable. And it has a universal property with respect to some squares where you start with not repeated objects. So I don't want to like derail us too much into coends. There are lots of examples of coends that people naturally think about. Like if you've got some bimodules over a ring R and you want to form their tensor product, then this is sort of trying to make the right action on M and the left action on N equal. And this can be expressed as a coend. The geometric realization of simplicial sets is kind of visibly a coend because you're just trying to glue some geometric simplices together using the simplicial set data. And if your category is co-complete, then we can just write down a formula for the coend, which is this co-equalizer of a pair of coproducts. So the first coproduct is over all the morphisms in your category, and the second is over all of the objects. And the two arrows there sort of using the morphism F, either pre or post composition. So I want to take the functor F, which takes a pair of objects in our category C that we think of as comodules, so F of V comma W, and it's just going to tensor together W and the dual of V. So this is a functor from C op cross C into finite dimensional vector spaces. Now the category of finite dimensional vector spaces doesn't have this coend, but that's okay because the category of vector spaces does. And the most basic version of Tannaka reconstruction is that if C really were the category of finite dimensional co-modules over a co-algebra, then taking the co-end of this thing would give you back that co-algebra. And furthermore, this procedure can tell you about structure on A. So what does that mean? It means that the functor u that you started with has structure exactly when A has some structure. So an example of this is that A is a bi-algebra if and only if this forgetful functor u is a strict monoidal functor. So it's an interesting exercise to take the strict monoidal structure. Well, it has to also be on C, that has to have a monoidal structure, and be compatible with the monoidal structure on vector spaces, and then get back the rest of a bi-algebra structure, which is to say a co-multiplication and a co-unit. You can get other things if you want by putting some other structure on the category C and the functor u, depending on what you're interested in. So I don't want anybody to get like too interested in the co-algebra co-module versus algebra module distinction. Those are not particularly relevant. So I've written this out in the kind of algebra and module version instead. So if you've got modules over an algebra and the forgetful functor, well, that basically is the same data as having the algebra itself. But this theorem says that if you've got a monoidal forgetful functor, really strict monoidal, then you get some more structure on your algebra, namely you get a bi-algebra. So I mentioned at the beginning that I wanted a thing called a tri-algebra, and so the question is like, what do I put at the bottom of this left-hand column? This is the thing David and I have been working on. So let me tell you a little bit about our higher dimensional Tannaka reconstruction project. So here is kind of the very broad view. So what do we want to do to make these things? Well, first, we just want to do some kind of like real basic, straightforward generalization of one categorical Tannaka reconstruction to two categorical Tannaka reconstruction. Then we want to get this like detection of structure theorem. And in particular, what we want to do is we want to set things up in a nice functorial way so that the functoriality somehow just spits that out automatically. Then, in order to get this notion of a tri-algebra, we're going to have to do reconstruction twice, and then I'll tell you a little bit about some examples and how they relate to TQFTs. So, how do we do this? Going from the one-dimensional version to the two-dimensional version, you just put a sort of 2 in front of everything. So instead of having co-algebras in a monoidal category, you've got kind of pseudo co-monoids in a monoidal 2 category. There's nothing particularly new at this level, except that it's a lot harder, as it usually is when you go up to kind of 2-dimensional things. And I was shocked at the number of kind of interesting and yet arbitrary choices that we had to make to even like get the project going, because things like, what is a dual supposed to be? Well, we know what a dual is supposed to be, but if you've ever worked with kind of monoidal 2 categories or 3 categories or anything like that, it's nice to have some theorems that say, well, you don't have to do the most complicated fiddly thing. You can do an easier version and it still works, but we don't know those things here. So at the moment, we've kind of proven what we can and made some arbitrary choices for the rest. But there are a bunch of interesting kinds of coherency questions that are already lurking right here. In ordinary Tannaka reconstruction, we had this co-end that we know how to deal with. So that gets replaced with a co-descent object, which is like a fancier version of a co-equalizer with some more things. There's not like a difficult thing that happens there. These kinds of constructions happen all over kind of 2-monad theory. So this is an obvious place where we know how things are supposed to go. And this is kind of what we basically know and are finishing writing up right now. Now, I said that we wanted this detection of structure result, and I wanted to do it as a consequence of setting up the basic theory the right way. So reconstruction is a thing that fundamentally takes an object in a slice and gives you back something new. So it takes this category, which you think sort of co-modules, and it gives you the co-algebra. So that means we've got to get a reconstruction functor, which goes from like 2cat over the thing that replaces finite dimensional vector spaces and gives us back a pseudo comonoid in V. And an interesting feature, of course, that doesn't appear in the one-dimensional version is in the two-dimensional version, we have lots of choices for what the one cells can be between pseudo comonoids. Those are just the kinds of cells that you would find in between monoidal categories. So we have lax monoidal functors, oplax monoidal functors, strong monoidal functors, or strict monoidal functors. And so that means really we need lots of versions of these slices. And the thing that we've discovered is you absolutely have to have adjunctions sort of as your fillers for little triangles in a slice category. This is not a thing that that I've really encountered. The natural thing to do is to maybe have a triangle in a slice with a 2-cell going one way, but it doesn't work because of the way this codescent object functions. So we have 4 different versions of this, although they're sort of functionally about the same. And then the extra structure, so things like this like bi-algebra structure that we got, those things all come by considering the sort of external versions of the structure that you're interested in. So if you want to get a multiplication, then you think, well, there's a multiplication from kind of the comodules themselves back to comodules. So I give you a pair of comodules, I can tensor those together. And then that thing becomes a cell in one of these slices, and then you sort of apply the reconstruction functor to the whole thing, and that's how you get the multiplication on the pseudo comonoid. Okay, so I said what we want to do then is to get trialgebras, and that means you've got to reconstruct twice. So we're going to take a monoidal, now it's a 2 functor, we reconstruct it once, and that gives you a kind of categorified version of a bialgebra. And then if you reconstruct that again, you should get this notion of a trialgebra. So the pattern is like every time you reconstruct, you sort of turn a dimension into a multiplication or a co-multiplication, and they kind of swap back and forth. Now, there's an earlier version of a trialgebra that Hendrik Pfeiffer defined, which is a category internal to co-commutative Hopf algebras. He approached this from a very different point of view, and in particular, we wanted to get something single sorted if at all possible. So I'm interested later to see how his notion compares with what we're going to get. There's some things that are left to do. In particular, we haven't written down this kind of very element-wise description of trialgebras as like a ring with some extra operations. And there's also something that should be like a kind of tri-adjunction, and this is the version up from what Daniel Sheppy has studied in his formal theory of Tannaka duality. Those are some other features of this that we're not yet done with. So I wanted to talk a little bit about examples. I started with TQFTs. We don't know anything about the TQFTs. I think as soon as we get done with this, David is going to sit down and try to make a genuine TQFT that takes manifolds and gives you something, but we can't do it yet. You can cheat and find some examples by doing a kind of day convolution thing, but this doesn't.
You have seconds left already.
That's fine, because all I have to say is that there's one example that we do know of that people want in kind of mathematical physics, and that's these locally presentable K-linear categories, and that does seem to work. Now I'm done. Thank you very much.
Okay, thank you very much, Nick. Perhaps, I don't know if there is a very, very quick comment. Otherwise, we will leave them for the breakout rooms later. Okay, very good. We continue with the next talk in 1 minute, okay?